Hi, all. So, this past weekend, I mentioned that I would make a video about some of the stuff that I've been working on with Zigler. Zigler is my library, which lets you write inline Zig programming language inside of your Elixir. I created it because I think that Zig is a particularly good match for writing low level code that interfaces with your Elixir code, partly because their programming philosophies are very similar in many ways. And I just love the language. It's very easy to get cool stuff done. Looks like Zig is headed towards doing lots of multi threaded stuff with very high performance, which is something that I'm also really excited about. So, the last video, I talked about memory allocation and why Zig is really good because you can very nicely interface with the memory system of the virtual machine and be a good citizen of the virtual machine. And now what I'm going to talk about is one of the central problems with running low-level code inside the Erlang virtual machine, and also how Zig allows you to be a really good citizen and maximize the level of choices that you have, especially if you use my Zigler library. Okay, so the central problem with Erlang Nifs, or low-level C ABI code, is that the C ABI programming style is sequential and not interruptible, not preemptible. And when you write code for the Erlang virtual machine, it's preemptible. So that means there's lots of points in your code where the virtual machine can just say, okay, you're going to stop and assign the scheduler, which is basically your execution thread, a different function or a different process to be working on, and then come back to you later. So these two systems operate at sort of like different levels of different conceptual levels, and getting them to work correctly is really difficult. As a result, there's a huge warning in the Erlang manual for writing Nifs, or low-level code. Let me read it for you, a little bit of it for you. It is of vital importance that a native function returns relatively fast. It is difficult to give an exact maximum time that a native function is allowed to work, but usually a well-behaving native function is to return to its caller within 1 millisecond. This can be achieved using different approaches, and I'll discuss those approaches later. If the NIF call is too lengthy, this must be handled in one of the following ways to avoid degraded responsiveness: scheduler load balancing problems and other strange behaviors. So you really don't want that stuff. There are three main ways you can execute long-running NIFs. One is called the yielding NIF. The way that a yielding NIF works is that your C or C-style program runs a certain amount of code, and then it stops. It gives the virtual machine a callback function and says, I'm done. And then the callback function gets executed later when the virtual machine decides it's time for you to come back. This is really tricky, first of all, because you don't usually think of running C in a sequential, in a tail call fashion. This is effectively a tail called NIF, right? And so a lot of things that you might want to do, like store variables on the stack, that's just not going to be possible. You've got to figure out how to take your data and pack it into basically a resource that gets passed between the calls, and then sort of reinflated on the other side. And what's tricky about this is that the way that you pack data in your calls is effectively restricted because you can't just put anything into an Erlang term. You kind of can, but it's tricky. And that process is easy to mess up. And so I think that's the reason why a lot of people don't use this technique, even though it is the preferred technique. And then, of course, you have to be able to have control over your entire code. So if you're running some sort of C library that somebody else has written for something else, it's basically out of the question. Okay, so another option is called the threaded Nif. I think that this is kind of the second most desirable way of doing this. It's especially useful if, again, you're calling somebody else's C function, and they just you can't break it up. And what this does is it basically has the Erlang machine requisition an operating system thread for you, and then it runs your function inside that operating system thread, and then it's kind of your responsibility to send the information back to the caller. So I've wrapped this in Zigler so that that the thread that calls it is actually properly paused and doesn't have to do anything until it behaves with the scheduler because it's an Erlang process, and then it uses message passing to get that information back and communicate back that it's finished. And that's a valid strategy for doing this. The only problem is that why you might not want to do this in general is that spawning an operating system thread is a really expensive process. So if you really need like fast responsiveness, you're not going to get that with this. And the other problem is that maybe your operating system doesn't even allow your Erlang virtual machine to spin up threads. That's pretty rare these days, but it's definitely something to worry about. The last technique, which I think is what most people use, is called the dirty Nif. And so I believe that the Rustler package for Rust kind of guides you towards using this as your technique for long running Nifs. This is the way this works is that the Erlang VM will launch with a certain number of schedulers that it permits to not have sort of like aggressive breakpoints. And the major problem, I guess, that spinning this up and setting up execution on these dirty Nif schedulers is pretty fast relative to spinning up an operating system thread, but the trade-off is that you only have so many of them. And we'll kind of and it's also the case that there's two different types, IO bound, one for IO bound jobs and one for CPU bound jobs. So it's really tricky to kind of get this exactly correct. And we'll see the differences between running a dirty Nif and a threaded Nif in the demo. So in short, if you can't break up your code because, say, it's in a C library or some library that you don't have control over, these are your two options: threaded Nifs and dirty Nifs. More heavyweights spin up and stand down, and this one has finite concurrency or bounded concurrency. You can only do so many of them at a time. This is the most preferred way of doing things with the yielding Nif if you can, but I think like a lot of people don't. Okay, so let's go to the demo. So back in our playground, here is what's going to happen. I'm going to spin up an Elixir session with this special Erlang flag plus S1. And what that means is that only one scheduler thread is going to exist. And so the reason why I do that is to make sort of these effects more visible. So you'll really get to see what's going on and why these different techniques have so dramatically different properties. Okay, so spinning this up, I've got this function called spawn sleep, right? And what it's going to do is it's going to spawn another process, And on that process, it's going to run this, whatever this sleep function is, right? And then we'll just IO inspect the result. Before I even run this though, what I want to do is I want to just show you that if you're running Erlang code or Erlang or Elixir code, so we're going to do process.sleep, which is a built-in Elixir function. One thing to note is that process.sleep takes milliseconds. So we're going to let this sleep for 5 seconds. And then when I run this, it's going to spawn in another process. I'll get my control back to my terminal, and then I'll run some, math on the terminal, some silly math on the terminal. And then when this process has completed sleeping, aka 5 seconds later, it's going to spit out the result to the console, which is going to be OK in the IO.inspect. So that's just going to print it to screen, print OK to screen. Okay, so let's do this. So I got control back. I can do 3 plus 5, 8. I can do 4 plus 5. And then even though, okay, so 5 seconds later, we got that OK, and that OK came from the IO.inspect. Great. So this is kind of what we expect. Elixir and Erlang are highly concurrent systems, and so we really expect to be able to spawn a process, have it go do something, and then while it's doing its thing, do whatever we want to do. Okay, so what's going to happen if I do playground.spawn sleep? And I will caution that Zig's std.time.sleep works on nanoseconds, so I will be inputting this as microseconds. So we're going to have to sleep for 5 million microseconds in order to get a 5-second pause. So let's go ahead and run this. And I didn't get my console back. I'm typing furiously and nothing's happening. Oh, and there it came. So I got control back after the entire thing had completed. So even though this should, in theory, be executing in its own process that's concurrent to what's going on in the console, I did not get control over my console back like I did in the previous case. Now, why is that? When I jumped into the sleep function, I started executing this C code, and this C code basically hogged the entire scheduler and never gave it back to my console. And now remember, my console is running. This entire virtual machine is only running one scheduler. So when that resource is exhausted by this greedy C function, that's it. I don't get control back until it's done. Okay, so let's fix that situation. We're going to go ahead and run dirty CPU. And in Zigler, all you have to do to convert a function from being a normal Nif to a dirty Nif is just add the dirty CPU tag to it. All right, so let's let that compile. And just gonna run this again. And now you can immediately see that I've gotten control back, right? All I had to do is change that one tag, and then it returns the result at the end there, okay? So yeah, that's pretty effective. But the thing is that, remember, like I said, that dirty CPU or dirty CPU Nifs, there's only one of them. There's only one scheduler, one dirty CPU scheduler. And so if I run two of these really fast, we're going to see the first one come back after 5 seconds, and then I have to wait another 5 seconds for the second one to be scheduled and complete its task. So that was kind of a long delay, right? So 5 seconds, 47, 5 seconds, 47. Okay, so that is in contrast to threaded. So if I switch just to threaded, it's got to recompile. And then I run two of these in rapid. So again, I can do things while it's waiting, right? And then it finally prints out the result. But if I run two of these in rapid succession, you'll see them come back in rapid succession, because they're indeed running on separate operating system threads. So that's how you do, that's kind of the major difference between dirty CPU and threaded Nifs. Of course, like I said before, the trade-off is that there's a lot more heavy machinery going on in order to spin up that threaded system. Okay, now let's do yielding Nifs. So what I've done with Zigler is I've made it so that the seam between sort of the sequential C style code and the tail called version of yielding is sort of merged using Zig's built-in async functions, or Zig's built-in async functionality. So this function is a little bit more involved. Basically, I need to be able to like set this up and break up the work into several chunks. And the way I do that is by using the suspend keyword. And while I'm suspending, I call this function called beam.yield, which communicates back to sort of the framework that is used to launch this, that it has suspended, and it's time to reschedule the next call, reschedule the resumption of this function at a later time. A couple of details here. This beam.yield function can fail with an error, and I'll talk about that a little bit later. And then it also has a return value, and the return value is the environment of the function. That's maybe a little bit of a nitty-gritty detail about what you have to do to do Nifs. But for example, if you ever want to send a message to another process, you're going to want to use this environment variable, and you can't count on passing the environment variable into the function, because that might change from underneath you. So that's why I have that. Okay, so let's go ahead and first run this. One thing I'll mention though is that the way that the time is calculated is a little bit different, right? So it only sleeps between suspensions and resumptions. So while it's in this loop, it sleeps. So the virtual machine will actually consume quite a bit of time between giving this process its own slices. So you can't really count on that microseconds value to add up correctly to what you would expect. So I'm going to actually give it a considerably less amount of time to run. And then, see, you can do that. And then I got control back of my console, and then it did finally complete, and then inspect it, and then print the result out. So, this is kind of how you can use Zig's keywords, and also a little bit of sort of glue work to really make this whole process, convert this sort of maybe difficult tail call into something that preserves the stack and preserves all of your data, and makes it sort of easier to rational about traditional C-structured Nifs that you want to use in your programs. So, I think that this is really a testament to how Andrew Kelly and the Zig team picked a good set of async primitives. They're not just usable for the sorts of things that are Zig only. It was relatively easy to build a seam between Zig's async functionality and what you need to do to be a good citizen of the Beam virtual machine. But that's not all. I do want to show you one more really cool thing about this. And, again, this is all about being a good citizen of the Beam virtual machine. So what I'm going to do is I'm going to change this code. I'm going to change this code a little bit. And we're going to say, run a program that's doing something really heavyweight. So we're going to allocate some memory. And we're going to allocate 10 megabytes of memory for this one thing. And we're good Zig programmers, so we're going to defer the freeing of this memory. Okay. But we might also have made a mistake and forgotten to ever stop this this while loop. So this while loop is going to go on forever. It will never reach this return 47. Okay, so let's do that. First thing I'm going to do is I'm going to measure the memory. If you remember this function from my last video, it's basically the same. It just shows you how much memory the VM is consuming. So let's do this. 24 megs. Okay, now I'm going to spawn one of these functions. I'm also going to trap the PID equals. Actually, the number doesn't matter because we're just gonna run this forever. Okay, so now we're running, and then let's check the memory. Oh hey, 10 megabytes of memory have been consumed by this process. And then maybe we're like, oh, whoops, I forgot to increment elapse. Let's kill this process. So in Elixir, the way you do that is process.exit. We're going to exit PID, and then we're going to give it the reason kill. So that killed that running process. And the cool thing is that the memory was recovered. So how did that happen? Well, the way that I've instrumented these yielding Nifs is that this beam.yield will detect if the process has the sort of the calling process has died. So if the calling process has died, this beam.yield will know to throw, while it's being suspended, instead of on its next resumption, instead of returning the environment variable, returns an error, and then it catches return -1, and that allows you to clean up the frame of this function. So one of the cool things about the Beam VM is that you can hook things up to the process garbage collectors, or the resource garbage collectors. So when the resource associated with this running yielding Nif is destroyed because the calling process has itself been canceled, I can actually jump back into this function one last time and just do a good job of cleaning everything up. So yeah, that is kind of the sort of stuff that I've been working on in this new 0.7.0 release of Zigler. There's a couple of things that I still really want that need a little bit of cooperation from the Zig programming language itself. In particular, one of the things I would like to do is to merge stack traces between Zig and Elixir. So hopefully that'll be coming soon, either with 0.7.1 or 0.8. And then I've just got a few more little cleanup things that are on the docket, are on my issues list. And once those are done, I will probably go back to working on Selectrix and Mavis, which are my Elixir static type checking libraries. So hope you enjoyed this video and learned something about how Nifs work in Erlang and Elixir. And thanks for watching. I know this was a little bit longer, but I hope you thought that this stuff was cool.